Okay, you guys, I don't know if I'm really not really sure how to work this YouTube thing, so I don't know if anybody's even on here live. I have like a little person picture and it says 16. I don't know if that means anybody's here. Hopefully this thing's working and hopefully you guys can hear me, and hopefully when people view the recording, you can hear me as well. If anyone is on here live, can you type in the chat and tell me if you're able to hear? Actually, it says chat disconnected. I'm not sure why. Okay, well, I'm not on mute, so hopefully people can hear. I am trying to bring up the slides, so just give me a second. Sorry, I'm still getting used to this format, you guys, so we'll get going in just a second. Here we go. Okay, so here we are today, AMT 151 basic electricity. We're going to start talking about metric-based prefixes for electrical calculations. We'll talk about commonly used prefixes in electrical readings, electrical measuring symbols, conversion table. We'll go over a conversion table and some conversion examples. So here is a table of some of the quantities of measurement that we'll be using in electricity. Voltage, we measure voltage in volts. The abbreviation for that or symbol for that is a capital V. Also EMF, electromotive force, a capital E. But most often, I mean, we'll be using voltage, capital V. So voltage is the electromotive force or pressure that creates current flow in a circuit. We'll also be measuring current, which the symbol for current is capital I. And we measure that using amperes. And that symbol is a capital A. We measure resistance, the opposition to current flow by electric components in that circuit. So the symbol for resistance is a capital R, And the unit of measurement for that is in the ohm, measure it in ohms. And we have the ohm symbol right there. Whoops, shoot. And last, power, capital P, we measure power in watts, which is a capital W. I see, I'm getting like these notices for new subscribers. I don't know if that means you can view this channel or not. I don't see anything in the chat. I don't even know if it's working, but I'm just gonna keep going. Most commonly used prefixes in electrical work are, we have mega, which means 1 million. The symbol for that is a capital N. We're also measuring kilo, which the symbol is a lowercase k, and that stands for 1,000. Milli, lowercase m, means 1,000th, 1 over 1,000. And micro, this funky little U looking guy is the symbol for micro, which stands for 1 millionth, 1 over 1 million. Those are fairly common, and you will see those a lot. I think I'm not sure if it's in basic electricity or advanced electricity, we'll get into some picofarads, which is a large exponential connotation for just higher values of measurement. So a couple examples here. Kilo means 1,000. When used with volts, it is expressed as kilovolt. And a kilovolt means 1,000 volts. The symbol for kilo is the lowercase k. 1,000 volts is 1 kilovolt. And this is written in a formula as 1 kV. Also, as an example, 1 volt would equal 1,000th of a kilovolt, or 1 over 1,000 kilovolts. So 1 volt here would be a writing of that using our symbols. 1 volt equals 1 over 1,000 kilovolts. Can also be stated as 0.001 kilovolts. That would equal 1 volt. So these two statements are equivalent. Milli, like we said, milli means 1,000th, 1 over 1,000. The symbol for that is a lowercase m. 1 millivolt equals 1,000th, 1 over 1,000, 1,000th of a volt. Also can be written as 0.001 volt equals 1 millivolt. So knowing how to convert metric prefixes back to base units is needed when reading digital multimeters or using electric circuit formulas. So sometimes we're reading, we're measuring and reading electrical readings, and maybe we're reading it in kilovolts, and we want to know how many volts that is, or we're reading it in kiloohms, and we want to know how many ohms that is. Here is a larger metric prefixes table. So we have milli, which written in scientific notation or multiplication factor is 10 to the negative third power. Here we have micro, same thing, negative 6th power, because micro means 1 over 1 millionth. And we go all the way up to pico, 10 to the negative 12 power, all the way through tera, 10 to the positive 12 power. These are the different symbols for those. Here we have, we'll see micro a lot, milli, kilo, mega, pico and nano. There will be some formulas that you'll see, especially on your written test. Well, on your written tests or your practice exams, you'll see those. And these are some examples of converting some of these prefixes to base units. Here we have example 1. Okay, so to convert amperes or amps, capital A, to milliamps, we would move the decimal point 3 places to the right. This is the same as multiplying the number by 1,000. Conversion steps for that example. So let's say we take 450 milliamps and we want to know how many, oh, I didn't catch you guys up. Okay, so here's conversion steps for, that's not the right slide. I'm not on the right side. Okay, so here we have 0.012 amps, and we want to know how many milliamps that equals. So conversion steps for that. We take 0.012 amps, and we move the decimal 3 places to the right. Here we have the decimal. 0.012 amps. We're going to take this decimal and move it 3 places to the right, which would put it at 0012.0. So that would equal 0.012 amps is the same as 12 milliamps. Remember, milli is this lowercase m. If we were dealing with mega, we wanted to know how many mega amps it is, it would be a capital M. Another example, to convert milliamps to amps, we would move the decimal point 3 places to the left. This is the same as multiplying by 0.001. Okay, so now in the example before, we were taking amps and we wanted to know how many milliamps it was. Now we're taking a certain number of milliamps and we want to see how many amps it is. So don't get it confused. It does matter which way you're converting it because it makes a big difference. If you are converting amps to milliamps, you're going to multiply by 1,000, which means you're going to move the decimal 3 places to the right. But if we are converting milliamps to amps, you want to move the decimal three places to the left. Okay, so conversion steps. Here we have an example of 450 milliamps. We want to know how many amps that is. What's that equal to in amps? So 450 milliamps, we're going to multiply by 0.001, which is the equivalent of moving this decimal 3 places to the left. So we take this decimal, 3 places to the left would make it 0.45 amps. Like we have here. Oops. 450 milliamps is the same as 0.45 amps. Example 3, we're going to convert volts to kilovolts. Okay, so I also wrote it in a different format here. This is something that I personally like to use. I tend to be able to convert it more if I'm looking at it as a math problem instead of trying to remember all the which way the decimal moves and stuff like that. So if we're trying to convert volts to kilovolts, we said we know that we have 1 volt, but we want to know how many kilovolts that equals. So if I treated this like a math problem, I would solve for kilovolts. I would want to get everything on one side of the problem. I would want to isolate kilovolts, and eventually that would give me how many kilovolts that would I'm sorry, that I said that wrong. I have 1 volt. I want to solve for kilovolts. So I'm going to take this as if it's a variable. If it's like, say it's X, you know, X kV, I want to divide by X and get everything on one side in order to solve for kilovolts. So that's something that I use, and you can use it or not. We move the decimal point 3 places to the left when we're converting from volts to kilovolts. So here's an example of that. We have 47,000 volts. We want to know how much that is in kilovolts. Okay, so if we take the decimal, we're going to move it 3 places to the left. So we have 47,000, move this decimal, it's going to become 47 kilovolts. Okay, because we said 1 kilovolt is 1,000 volts. So if I divide 47,000 by 1,000, that's going to give me 47 kilovolts. That's how much 47,000 volts is in kilovolts. Example 4, to convert megohms. Here we have megohms. Remember, mega is million. We want to convert it to ohms. We would move the decimal point 6 places to the right because we would be multiplying by 1 million. So if we're multiplying by 1 million, that's a whole number. We're going to move the decimal place to the right. If we were multiplying by 1 over 1 millionth, which is micro, we would be multiplying by 0.000001, 6 places to the left. Okay, so an example of that, the conversion steps. Let's say we have 2.2 megohms, and we want to know how much that is in ohms. So here we are, we have 2.2. We want to take that decimal and move it 6 places to the right. That's going to give us 2,200,000 ohms. So 2.2 megohms, written in ohms, is 2,200,000 ohms. It's much easier to say 2.2 megohms rather than always write this everywhere. One more example. In here, we're converting microamperes to amps or amperes. We move the decimal point 6 places to the left, just kind of like I said before. Okay, so microamps is 1 millionth. That's 1 over 1 million, and mega is 1 million. So if we were going to treat that as a math problem, we would take 1 amp and multiply it by 1 over 1 million if we wanted to convert to microamps. So here, let's say we have 500 microamps. We want to know how much that is in amps. So if we want to know how much that is in amps, we would take 500 and move the decimal 6 places to the left, which in this second step here, you can see the decimal point on 500 would be over here. If we moved it 6 places to the left, we would be at 0.0005 amps. Okay, so 500 microamps is the same as 0.0005 amps. Okay, so these are actually some questions for you guys. I kind of made these slides as if we were in a live lecture where you guys could answer these questions on your own. So I'll just go through them with you. These are some examples of questions that you would see in your written exams. So they might ask you something like, what is the base unit and symbol used for electric? And there's some examples here. Sorry, I'm just trying to check if I can tell if this thing's working at all. But I guess we'll just have to tell once I post it. Okay, so what is the base unit and symbol used for electric resistance? So what that's asking is for resistance, what's the base unit and what's the symbol used? Okay, so when we're measuring resistance, the base unit would be ohms, and the symbol for ohms is the ohm symbol. So how about what is the base unit and symbol used for electric power? If you guys remember at the beginning, one of the very first slides, the base unit for power was watts, and the symbol for watts was a capital W. So what is the base unit and symbol used for electric current? Current was measured in amps. And the symbol for that is a capital A. What is the base unit and symbol used for electric voltage? So what do we measure voltage in? We measure voltage in volts, right? Some of these are pretty simple. And the symbol for that is a capital V. Okay, and these are some more examples that you could see in your written exams, but there's not a lot of questions on just writing metric prefixes. Your written exams will have more complex questions. I'm sure you guys have looked through the ASA. There'll be something like reading certain diagrams and trying to express what the units of measurements are or stuff like that. Okay, so write the metric prefix and symbol used to represent each of the following. So what do I mean when I say metric prefix? Well, at the beginning of this lecture, that's what this is all about, metric prefix. So the metric prefix is that word before amp or before volt. So if we want a kilovolt, that's the prefix is kilo. If we want a millivolt, the prefix is milli. Okay, and then what the symbol is for that. So do you guys remember what the symbol is for micro? Okay, so write the metric prefix and symbol used to represent each of the following. So 1,000. Which of those prefixes stood for 1,000? 1,000th is 1 over 1,000, not to be confused with 1,000. So 1,000th was milli. And the symbol for that was a lowercase m. Okay, the metric prefix and symbol for 1 million. 1 million as a whole number, the metric prefix for that was mega. And the symbol, capital M. And 1 millionth, meaning 1 over 1 million, was micro. The symbol for that was that funky little U. And 1,000, 1,000 as a whole number, the prefix for that was kilo and the symbol lowercase k. Okay, so if we were going to use some more examples that you guys could do on your own, I made a list, and you guys, when you guys have these slides, you can go through and see if you can do these on your own. The answers are on the slides as well, so you know, just as practice, what I would do, what I did do in school is I would take some of these and I would, you know, see if I could get to the answer myself and then double check yourself. So if we were going to convert 2,500 ohms to kiloohms, what would we do? Okay, so that's something that you could practice on your own. You would want to convert 2,500 ohms to kiloohms. So if we were converting to kiloohms, kiloohms is what? Kilo is 1,000, right? 1,000 as a whole number. So we would divide 2,500 by 1,000. That would give us 2.5 kiloohms. 120 kiloohms to ohms. So if we're going from kiloohms to ohms, we're going to convert This is 120,000 ohms, and we want to find out how many ohms it is. Well, we know that 1 ohm is 1,000 kiloohms. So this would make this 120,000 ohms. Because that kilo, that I keep saying kilio, but it's kilo. Kilo is 1,000, so we would multiply the 120 and just write it out. That's how many ohms it is. But instead of writing 120,000 ohms, it's a little more shorthand to write 120K, you would put K and then the ohm symbol instead of writing out kiloohms. It's, a little more shorthand when you're doing these long electrical problems. You can just write 120K ohm. Okay, we're going to convert 1,500,000 ohms to megohms. How would we convert that? Mega is 1 million. So if we're converting to megohms, we're going to divide by 1,000,000, which would give us 1.5 megohms. That's a lot easier to write than 1,500,000 ohms. Converting 2.03 megohms to ohms. So going the other direction from megohms to ohms, we would move the decimal point 6 places to the left. I'm sorry, 6 places to the right, megohms to ohms. So 2,030,000 ohms. It's a lot easier to just write 2.03. So we want to find out how 2.03 megohms, we want to find out how much that is in ohms. So that's shorthand. This is the shorthand version for 2,030,000 ohms. Okay, if we want to convert 0.000466 amps to milliamps, how would we do that? Milli means 1,000, right? So we would be multiplying by 1 over 1,000. That's going to move the decimal point 3 places to the right. And it would give us 0.466 milliamps. How about 378 millivolts to volts? So what we're asking is, we have 378 millivolts. How much is that to us if we wanted it in volts? Well, millivolts is 1 over 1,000, right? So if we wanted to convert that to volts, we know that 1 volt equals 0.001 millivolts. We would move the decimal point 3 places to the left, which would give us 0.378 volts. 475 ohms to kiloohms. Kiloohms is 1,000, right? 1 ohm equals 1 ohm in kiloohms equals 1,000 ohms. So in kiloohms, we would move the decimal point 3 places to the left, or 0.475 kiloohms. That's how many kiloohms 475 ohms is. 28 microamps to amps. So microamps is in 1 over 1 million, 1 millionth. So we would multiply that by we multiply 28 by 1 over 1 million. And that would give us 0.000028 microamps. I'm sorry, amps. That's converted to amps. This little micro symbol shouldn't be there. So that's how many amps are in 28 microamps. So it's a lot easier to write 28 microamp than 0.000028 amp. I'll try, if I can remember, I'll correct that before I post the slides tomorrow. Okay, and this is more like something that you might see on a written test. They would give you 5 kiloohms, and then they would give you some type of reading in just ohms, and they would want you to convert it to one measurement or the other. Okay, so if we take 5 kiloohms and we want to add it to 850 ohms, and then we want the whole thing converted to kiloohms, how would we do that whole equation? Well, the easiest way to do that is if we know that we have 5 kiloohms, kilo meaning 1,000, then we would just multiply 1,000 by the 5 kiloohms. So that would give us 5,000 ohms. So that converts both of these, the 850 and the 5, into ohms instead of 1 kilo and 1 ohms. Okay, so now we have 5,000 ohms plus 850 ohms. That gives us a total of 5,850 ohms. So if we want to convert 5,850 ohms into kiloohms, we're going to move the decimal point 3 places to the left. So that would give us 5.85 kiloohms. So that's a good problem to use as an example for something that will continue to build on these prefixes and equations. I think I have a few more examples here. Okay, 40,000 kilovolts to megavolts. So this is also something that you might see. You're not always going to see 40,000 volts to kilovolts, or 30,000 volts to megavolts, or 30,000 amps to microamps. Sometimes you're going to see a lot of starting at one base unit and trying to move up to one that's larger or smaller. So kilovolts we know is 1,000, kilo 1,000. So we have 40,000 kilovolts, but we want to know what that is to us in megavolts. Megavolts being 1,000,000. So if we had this, kilovolts is would be 10 to the power of 1. And megavolts is 10 to the power of 6. I'm sorry, kilovolts is 10 to the power of 3. Megavolts is 10 to the power of 6. So if we take the difference of those exponentials, we have 10 to the power of 3. So what we're going to do is move this decimal point 3 places to the left, which would give us 40 megavolts. That's what 40,000 kilovolts is to us in megavolts. We would take that decimal point and move it 3 places to the left. So that's another good example to get an idea of, because it can be confusing going from kilo to mega or kilo to micro, because you're not going to be, you got to take the difference of those exponentials. So here we have 4,600,000 microamps. We want to convert that to amps. So what's that to us? That we would take the decimal point and move it 6 places to the left, 4.6 amps. Okay, so if we got a reading, 4,600,000 microamps, and we needed to write that in a logbook somewhere, we would want to convert that to 4.6 amps because it's much easier to read. 2.2 kiloohms to ohms. So if we wanted to convert that to ohms, we would move the decimal point 3 places to the right, 2,200 ohms. And here is an answer key for those questions. Just if you guys want to practice those, like I said, these slides were made to kind of do a little more interactively. So you could always write those down on a piece of paper and then go back and check this answer key, make sure you guys are getting those answers. I'm going to move on. So that's all for my metric prefixes. I hope that gives you guys a general idea of some ways to come about those equations, because we're going to be dealing with a lot of those readings. A lot of this class is using multimeters and measuring resistances and stuff like that. You need to be able to have correct readings to know that you're doing it right. We have static electricity. So why does static electricity matter to us in aviation? Oh, I get kind of sick of talking up here. Okay, so static electricity, we're going to talk about static versus dynamic electricity, the differences and characteristics of both of those. ESD, electrostatic discharge. That is a very big component when dealing with any electrical equipment, not just aviation, but you know, computer guys deal with ESD and the hazards that causes to the equipment, more so than ourselves, but also to ourselves, something that we need to be aware of and keep the equipment working properly. And safety precautions especially regarding ESD. So static versus dynamic electricity. I made you guys this cool little table. Remember Baby Genius? You're welcome. So here we have static. So the differences between static and dynamic electricity, some of the characteristics of these things. Static electricity, the first one up here. The difference between static and dynamic electricity as it relates to electrons. Static electricity, electrons are electrons at rest. Dynamic electricity electrons are electrons in motion. In static electricity, we don't have any current flow. Static electricity doesn't carry a current. Static electricity is a buildup of electrical charge on the surface of an object. So it builds up especially when two objects can build up that charge off of each other when they're rubbed together, when those two objects touch one another and they have this transfer of electrons, which is the last one here. A transfer of electrons causes an imbalance of charges between materials. So those are the characteristics of static. Dynamic electricity. Dynamic electricity can have an active flow of AC or DC current from a power source. Static electricity cannot. So an active flow of current of AC or DC electricity from a power source would mean that we're dealing with dynamic electricity. Dynamic electricity also can flow in an electrical circuit. Static electricity cannot. Some examples of static electricity, of course, lightning. Lightning is a buildup of static electricity, and then it's released with this, heating up of the molecules that release this charge, and that's where we get the lightning from. The color of lightning, that big like zap. So lightning is a big one for us in aviation as well, because we're a big metal object flying through the air. We accumulate a lot of static electricity, and we also don't want to get hit by lightning, which is a buildup of static electricity. Which in NAVCOM, you'll learn more about some of the equipment and precautions used on aircraft in order to deal with lightning, if or when it happens. I have this cool little video. Oh, good, it's gonna work. It's like a slow motion of lightning hitting a plane. I thought it was pretty cool. This is like the slow motion part. It's pretty crazy. I thought that was a cool video. What are we talking about? Static electricity, yeah. So we all know the common, rubbing the balloon on the hair. I like this picture because it has a dog. Little doggy. Transfer of electrons. This is the transfer of electrons between these two materials, creating this static electricity. Animals can also be carriers of static electricity. This is a picture of a saltwater electric eel. I think they're actually like 10 feet long, but not like, this isn't a marine biology class, just interesting fact. Stingrays, there are some stingrays that carry static electricity. So those are some examples of static electricity, some examples of dynamic electricity, batteries. So we use a lot, in this class we'll be using, talking about batteries a lot more in the second portion of the semester. But batteries are an example of dynamic electricity. That's our power source. Our power source can carry a current flow, to all the components that we need. An extension cord. An extension cord is a carrier for dynamic electricity. We plug this in and the current can flow through that cord to whatever we need it to. And electrical circuits. Our electrical circuits are an example of dynamic electricity. Which one do we deal with more in regards to aviation? Well, we deal with both of them the same, I would say. We deal with static electricity because when we're flying through the air, the plane builds up a lot of static electricity, and that static electricity needs to be dissipated somewhere and needs to be dissipated safely. So we have certain components that can do that. We also deal with static electricity with regards to lightning and how that can affect the plane and how we safeguard that. And we deal with dynamic electricity like our batteries and everything that flows through components in the aircraft, everything that's electrically operated. ESD, electrostatic discharge. This is a very important topic, especially when dealing with basic electricity class. When we're working on planes and engines and pulling off components and putting new components on or shipping components, there's always the potential for electrostatic discharge to damage those components. So we'll talk about how electrostatic discharge is one of the most frequent causes of damaged electrical components. Damage can occur if technicians have poor handling practices. And never touch the mating pins of connectors, and always cover those types of components with ESD cap covers, which is these. That's the picture right there. So I blew up that same picture to show you guys these little red arrows are pointing at this little triangle symbol. It's a little hard to see, but you can probably see it. All of them have them if they are ESD caps. It's like a little triangle with a hand, and it's like crossed out because that's the symbol for ESD. We don't want your hand touching the mating pins in here. So the problem with that, if we touch the mating pins, the electrostatic discharge that builds up, the electrons that build up from us all day walking around on carpet and touching door handles and all of that, if we touch the mating pins of these components that have these connectors, we could be sending a transfer of electrons through electrostatic discharge, and we could be damaging internal components of that machinery that could cause damage that we might not even know. And that's not good. This is another little video because I get sick of talking up here. So this is going to talk about electrostatic discharge and how to protect against that, and these cool little ESD mats. We actually had these ESD mats when I worked at Disney. Disney works with a lot of electrical components, as you can imagine, with all of their animatronic stuff and all the animatronic stuff that's in the roller coasters. So all toolboxes that had electrical tools had these ESD mats on top of them, and you're supposed to wear this bracelet. It grounds you to the mat, and the mat doesn't allow for any transfer of electrostatic discharge between, say, the toolbox and that component, or your tools and that component, stuff like that.
Over there. Hey, what's up?
I'm finishing up lecture. They can probably hear me. Okay, so that explains some information to you guys about ESD, electrostatic discharge. And the last thing that we'll go over is some precautions that should be taken when working with electronic components. This comes directly from your book, the 8083-30. It's in the beginning of the basic electricity chapter, page 10.7. Page 10.7 in my version. If you have a more updated version, I think it changed to chapter 12, but whatever your chapter is. Always connect the ground between test equipment and circuit before attempting to inject or monitor a signal. Ensure test voltages do not exceed maximum allowable voltage for the circuit components and transistors. Ohm meter ranges that require a current of more than 1 milliampere in the test circuit should not be used for testing transistors. The heat applied to a diode or transistor when soldering is required should be kept to a minimum by using low wattage soldering irons and heat sinks. Do not pry components off of a circuit board. We won't really be doing anything with circuit boards, so. But don't pry electrical components. Power must be removed from a circuit before replacing a component. That's always a good practice. When using test probes on equipment and the space between the test points is very close, keep the exposed portion of the leads as small as possible to prevent shorting. Okay, so that's it today. That concludes lecture for August 31st. Don't forget to take the lecture quiz by midnight tonight. And the slides will be available tomorrow. I'll have them downloaded. I will see you guys for lecture at 4:30 on Wednesday.